the interesting application that we have for series and sequences, those number patterns, actually comes from the area of finance. And before the website sucked all the fun out of it, you could use these to work out things like loan repayments. Now you just punch a number into a website and go, bang, oh, here's the answer. I can honestly say I used these when I was, again, back in the dim, dark 80s, when I was working out whether I could afford to take out a loan and things like that. I actually would use the maths formulas to work it out. Let's really go back to the start of finance, into that little thing called simple interest. Called that, of course, because it's very simple. So the interest is PRT. I stands for the interest. P is the principal. No, not Dr. Bathgate, but the amount of money you have. And R is the interest rate written as a decimal or a fraction if you want to. I mean, either way is fine. And it's just a very simplistic way of doing it. T, of course, is time periods. $3,000 invested for 7 years, 6% simple interest. How much will it be worth? Well, we work out the interest, PRT, so 3,000, 6% is 0.06. 7 years, $1,260. Of course, that doesn't answer the question. Make sure you read the question, know exactly what they're asking for. They want to know how much it would be worth. So we would have to add that on to the principal, and it's now worth $4,260. To the best of my knowledge, simple interest is actually illegal to do in reality. Okay, well, it's not fair. Compound interest is a much fairer thing. So let's look at that, the compound interest formula, and we'll see why we look at it in this topic of series. There's the formula for compound interest. It looks very familiar when I write it that way. And you remember the general term for a geometric pattern is AR to the n minus 1. Well, it has that same feel to it. P, so some constant, times a rate to the power of, all right, they've got n instead of n minus 1, but it's exactly the same formula. Okay? So it actually is the general term of a geometric series. AN. With this formula, of course, you don't have to add on the interest. It works it all out for you. So it's the final amount after n time periods. P, again, is the principal. Now for R is 1 plus the interest rate. So not just the interest rate. Again, decimal or fraction, up to you. And n is the number of time periods. But for this formula, it's important that we make sure they match. Because how often it compounds is very important. It's got to match that. So let's do the same question, but now we'll say, oh, it's compounded annually. So we sub it into our formula, 3,000, 1.06, power of 7, because it's annually, and we get 4,510.89. What was our answer for the simple interest? 4,260. So you can see, just in a relatively short amount of time, if we talk about an investment, 7 years, and already you're way ahead of that simple interest idea. Hence why I think it is actually illegal to use simple interest. So if we were to compound monthly instead of annually, same formula of course, but we've got to change our interest rate because that's quoted at per annum. We want that per month. Oh, what's that lucky? 6. That divides by 12 nicely. And we get 1.005, but now it's not 7 years, it's 84 months. By the way, this is where sometimes I'll use fractions instead of decimals, because if that interest rate is not something that divides nicely, then I'll just write it as a fraction over 12, do something like that. And we get 4,561, so not a lot more, but by compounding monthly, we get an extra $50 or so. Depreciation really is exactly the same thing, but instead of it growing, it's decreasing. So same formula, it's just that when you work out R, it's now 1 minus the rate, because the value is going down instead of the value going up. But other than that, it's exactly the same. So let's have a look at this one. An espresso machine. I'm told that's a coffee machine. Don't drink coffee myself. Ooh, horrible habit. Okay, $50,000. That's one heck of a coffee machine. $15,000 on the 1st of January 2001. I guess that's just to make the maths nice and easy that the first year was and one. It depreciates at 12.5% per annum. What's its value going to be in 2010, 1st of January? So there's the formula. 1 minus the 12.5%, so we get 0.875. It's to the power of 9, and there's our value. Whoa! So in 9 years, it was 15,000. It's now only 4,500. Yes. I suppose a 9-year-old coffee machine. During which year will its value drop below 10% the original cost? So we want to know, there's our general term, we don't know what n is. Notice it's power of n, not n minus 1. Right? So common mistake is to go n minus 1 because we're so used to geometric series. We want to know when that's less than the 10%, or 10% would be 1,500. So divide both sides by, what a surprise, we get 0.1 because it's 10% of the value. Now we have to solve this inequality. Logs, looks like we're going to use. Log both sides, bring the n to the front, divide by log of 0.875, but that of course is a negative number, any log less than 1. So change the sign, you change the sign. So 17.24, they're saying during which year? Now, the reason I point that out because it's tempting to say 17 because you round down, but remember it's saying n has to be bigger than 17.2. So you can't round down to 17. It's not going to have happened at 17. So it must be when it was 18. So the 18th year, which is this year. I wonder if they're still using that espresso machine. Here's the more interesting application of all these, which really does, as I say, used to before the internet, have some real world values to it. 2002, you see I've got to go quite back in time here. Question 9b. A superannuation fund, interest of 8.75% per annum, compounds annually. Stephanie decides to invest $5,000 at the beginning of every year, commencing on the 1st of January 2003. What will be the value of her superannuation when she retires in 20 years' time? Wouldn't that be lovely if you could just retire after 20 years of work? We can dream. All right, 4 marks. Of course, this is just a model of superannuation. In reality, that's not how superannuation works. You don't get a fixed percentage. The percentage will change from year to year. Putting in a consistent amount each time, I mean, that's what you do with superannuation, but the actual interest rate will change. But as I say, just a simplified version to get a feel for what's happening. So let's have a look at that first investment. So it's just compound interest. First investment is in there for 21 years, and the interest rate 8.75. So we just work out that investment. The next year is going to come along, and we're going to put another 5,000. It's only going to be invested for 20 years. So that would be compound interest, how much it's going to be. Then the next year comes along, but that'll only be in there for 19 years. And so on and so on and so on, till eventually we're going to put $5,000 in, which will only be in there for 1 year, because then we're going to retire and we'll take all the money, thank you very much. So the last one will be in there for 1 year. Well, we get all of those added together. So our final amount, and you can see now we have a geometric series. We just want to work out the value of this series. Okay, well, A, the very first one, I'm sort of reading it backwards, so the lowest power first, but the very first term is 5,000, 1.0875. The ratio is also 1.0875, and the number of terms are 21. So all we've got to do is put that in our sum to n formula. Going to be sum of 21 terms. So A, 5,000, 1.0875, times R to the power of n, 21, minus 1 over 1 minus R, 0.0875. Punch the buttons in our calculator, very carefully of course. And there it is, 299,604. Wouldn't it be nice if that was enough to retire on? Not even close. Okay. Now, this question wasn't actually in the HSC. That's why I put an asterisk there. I've just added it to the question. Well, when would it first exceed 200,000? People look for round figures. They go, I wonder when I've got this much money. So when would I get $200,000 for this fund? So all right, this time we don't know what N is. But we've still got the same pattern. It's going to be power of 1, power of 2, up to whatever N is going to be, which is what we're trying to find. So it's still the sum to N, but this time we know the answer. The answer is 200,000. So we want to know, when is that going to be bigger than 200,000? So again, we put it in our sum to N formula, but this time we just don't know what N is. We want it to be bigger than 200,000. Solve the inequality. So if I multiply both sides by 0.0875, divide by the 5,000, it actually turns into a neat little fraction. 280 over 87. Probably a good idea to move the 1 to the other side. 367 on 87. Again, we got a situation where it's in the power, so I'll log both sides. Bring the N to the front. Divide by, well, this is a log bigger than 1, so it's not going to change sign. So whatever this is, log 367 over 87 divided by log 1.0875, we get 17.160 and so on. So, well, the first whole number there would be 18. So it would be 2021 would be the first year. Always interesting how you answer these questions. Because do I say, oh, it was the 18th year, or do you actually name the year, or, I guess it doesn't matter as long as it's very clear. I still would be writing the N equals 18 down, so it's clear I know what the answer is. How I interpret that answer, hopefully, is then correct. Here's another one added in. Let's change the question again. 200,000, no, we don't want 200,000. We'd like $1 million. That's that number that everyone goes, oh, I'm a millionaire. I still want to retire 31st of December 2020. I want $1 million. So how much do I have to invest to do that? So it's the same problem, but this time I don't know what the principal is. But we know there's going to be 18 investments all up. Is that right? Yes, because it's by 31st of December 2020, because the 18th investment will happen on the 1st of January 2021. So we would assume that the day before we would have got to the, So the first term is P, whatever P is, 1.0875, ratio at 18. So we said, when is the sum to 18 $1 million? It looks horrible, but really it is quite a simple equation when you think about it. I've just got to multiply by the denominator, get rid of that, and then divide by the two factors in the top. And there's my answer, whatever that turns out to be. More useful if we actually calculate it out, get some sort of feel for it. Well, we couldn't get away with, what were we investing? $5,000? We want $1 million? Yeah, just a little bit more than that would get us $1 million. Almost $23,000 a year. What's that a month? It's got to be just short of 2,000, doesn't it? 2,000, yeah, okay. You'd need a reasonable wage to be able to afford to invest $2,000 a month, wouldn't you? Loan repayments. This is the one that I found very interesting when I was trying to work out whether I could afford to get a new car, something like that. So this time, the amount owing. Right? So how much do I still have owing? Now this little idea, using this idea, makes, I think, it a much easier way to think about it. So we say, how much do I still owe? Well, how much will I still owe will always be the amount that I've borrowed and the interest rate applied to that, minus the amount that I've paid back with the interest rate applied. Because when you think about it, what it is two different sets of investments. The loan that the bank is giving me, they're investing in me. So I am paying them interest. Okay? And so it's like I'm a bank now and I'm giving them compound interest. But then the money I give back to the bank is like me investing in the bank. And so they pay me compound interest on the money I'm giving them. Okay, so they've now got my money with interest rate applied, and we subtract the two. And it's not until that difference becomes zero, we both go, great, we're even. We'll leave it there, thanks, we're done. Yeah. So here we go. Richard and Kathy, they borrow $20,000 from the bank to go on a holiday. Interest is going to be 12% per annum. Oh, 12, what do you know? Compounded monthly. They start repaying the loan 1 month after taking it out, and they're going to pay back $300 each time. Okay. So the first question is, how much will they owe at the end of 6 years? So the first part is the borrowing. How much is the bank going to make? So 20,000, 1.01 to the power of 72. Remember, this is in months. Okay, so that's the bank investing in me. Now, so just think of repayments, as I say, isn't it? It's another investment. You're investing in your loan. So the first repayment, it's now just like the compound interest, the superannuation idea. My first repayment, we're calling it a repayment, but it's really an investment. First repayment will be in there for 71 months. Because remember, you don't start repaying until a month later. I mean, it would be silly to repay straight away. That'd be like me saying, yeah, I'll lend you $20. Here you go. Can I have $2 back now, thanks? You don't do that. You wait a time period till you make your first repayment. The second one will be invested for 70 months, and so on until you're going to get the second last one. It'll be there for 1 month because your last one is in there for no months. Because once you make that last payment, you say, we're done. So they're not going to charge interest on it because you're even. So the last one's just the $300. Okay, so remember that idea. Those two investments, we subtract one from the other. So 20,000 minus our series, our compound interest idea, our superannuation idea, call it whatever you will. Well, that second one, again, is a pattern. First term's 300, the rate 1.01, number of terms 72. So we can sub it into our formula. Sub it in, bit of calculator work, and there we go, we come up with it. So $9,529. So remember, what did we just find? We're saying how much is still owing after 72 months, so 6 years. That's how much we've still got to go. That's the balance between how much they've invested in me and how much I've invested in them. Well, how much interest then have they paid in those 6 years? Well, we know they made 72 repayments of $300. So 21,600. So we're saying we've got 9,000 left to pay on the loan. But I've given them $21,000. So I've reduced the loan by $10,470. So hang on. If I've paid them $21,600, but I have reduced the loan, but the difference must be the interest then. That's how much interest I've given them. That's the extra money, if you like. So actually, for that $20,000 holiday, after 6 years, it better have been a good holiday. I've given them another $11,000. And that is the world of finance right there. The winner is the bank. Why these CEOs are getting paid incredible amounts of money and things like that. And it's why actuaries get paid very good money. Part 2. How much do we have to pay back? Let's find the amount of each instalment. It was $30,000. I might have rounded the numbers to make it nice. But $30,000, I wanted to pay it off in 5 years. So 60 equal monthly payments. The interest at the time was around 9%. So how much should it be? So this time, I don't know the monthly instalment. Okay? So I'll just call it M. That's how much I'm going to pay back. That's what I want to work out. But the initial loan, I know that's going to be borrowed for 60 months. So at least I know how much money I've got to give back to them, all up. Now, how much money are they going to give me? Remember the balance between? We've got to get it to 0. So the first repayment I make, I'm going to invest that for 59 months. Don't know what M is yet. Next one, 58. Okay, it'll be 58 months. So on and so on and so on. So the second last one will be times 1 and our last repayment. So amount N will always be the amount they invest in me minus the amount I invest in them. We just want to know what M is. Okay. A is M. You could do it two ways, really. You could factorise the M out. It still has the same effect, because if you think of the formula is A outside R to the power of N. Well, if you factorise the M out, then A is 1. So it doesn't really matter which way you do it. Okay, sub it into the formula. There it is. But hang on, we know an extra piece of information. We know we want it to be 0. We want that to balance out. We're even. Done. So we make that equal to 0. That's what we have to solve to find M. A little bit of manipulation. Move it to the other side. Multiply, divide. There it is in all its glory. Makes more sense if we come up with a number we could make sense out of. There you go. Turns out to be a monthly repayment of $622.75. Well, same situation, but this time I know how much I want to pay back. I know how much I want to borrow. I know the interest rate. How long is it going to take me to pay it off is what I want to know. Look, obviously they're dealing in big amounts of money as a council. They're borrowing, what's that, 3 million?
Yeah.
3 million. Ooh. At the beginning of 2005, year of the HFC. Annual interest, oh, look at that, 12%. That works out nice, doesn't it? Amazing how you get these nice, neat numbers you can play around with. Each year, interest calculated at the balance at the beginning of the year and added to the balance owing. Wow, that's a clumsy way of saying it. The debt is to be repaid by equal annual repayments of $480,000. Again, we're not talking about a person here. We're talking about a council, so bigger numbers. First repayment made at the end of 2005. Let AN be the standard thing. Now, first part of the question was simply show that the amount after 2 years is that. Okay. Well, we know the initial loan. There's the compound interest formula. The first repayment's in there for 1 year. So the second repayment, oh, that's it. They're the only repayments because we're only doing it over 2 years. So we find the difference between the two. And we've got it. Well, they've tried to make it fancy by putting in scientific notation. But if you look at it, that's what we've got. So bingo, we've got the answer. All right. Show that amount n ends up being 10 to the power of 6, 4 minus 1.12 to the power of n. Okay. Well, this time we don't know what n is. So, yep, there it is, 1.12 to the power of n. First repayment then, well, it'll be n minus, again, I don't know what n is, but it'll be in there for n minus 1 years. Then n minus 2, so on and so on and so on. Okay, let's create our little formula. Amount n will be the difference between the two. There it is. Well, it's not quite what they've got. Okay, well, let's see what happens. Let's do our formula. A is 480,000, or you factorise it out either way. R is 1.12, N is N. Sub it into our formula. Okay. Now, the numbers worked out quite nicely because 480,000 when you divide it by 0.12 is just simply 4 million. And so when you expand that out, oh look, common factor of 1.12 to the power of n. So I can combine those two together, and now we've actually got what they asked for because there's a common factor there of 10 to the power of 6. In which year will Wheelbarrow Council make the last repayments? All right, so when is amount n equals 0? Well, they're giving us a formula, so let's not worry about doing all that again. We've now got this neat little formula we can use. So we just need to solve that. Move the 4, log both sides, n to the front, divide by log 1.12. There it's 12.232507. So the 13th repayment. 13th repayment. Okay. All right. I just picked a handful of questions out of each of them.